Hello! In this short video I am going to explain some terms in vector algebra which are essential for programming games, such as velocity vector and its relation to speed, normalized direction vector, and displacement vectors. The most important point, however, is to avoid confusion between point and vector coordinates. They are both represented as x and y, or x, y, and z in the 3D space, and they can both be represented in the same way in a computer program, but still they are inherently different, and mixing them up is a guaranteed disaster. So here it is. We have a small vehicle in a prototype 2D game. It has its coordinates, in this case 8 and -4. There are absolute coordinates which can be easily read from the coordinate system. Changing the car's position whilst moving around will change the coordinates accordingly. Now I'm introducing the direction vector, or to be more precise, the normalized direction vector. That's this small blue arrow. It shows which direction the car is heading. It is important because it informs the system about the initial direction of motion when it starts moving. This vector is called normalized because its length, in maths we call it the magnitude, is equal to 1. The vector coordinates are 0, 1. This is because it is a small vector of the magnitude 1 and pointing up. These coordinates don't change when the car is moving, but they change when it's rotating, changing its direction. The pair of coordinates describes which way the vector is pointing. Let's go back to the initial position and rotate it to some nice direction like this. The direction vector tells us about the car heading, but doesn't tell specifically about its motion. The car still has some heading even if it is motionless, but if it gains speed, we can observe a new, very important vector. This is the velocity vector. It is always pointing in the direction of motion, so the blue direction vector and the red velocity vector will always overlap. But the velocity vector will change its magnitude with the speed. The faster it is moving, the longer the velocity vector, and the other way around. Let's now go back to the initial position, accelerate the car, and pause when it achieved its maximum speed. The velocity vector shows exactly how far and where you travel within 1 second. So now I will let it go for exactly 1 second, and it will travel towards the end of the arrow and stop exactly here. The length, or rather the magnitude of the velocity vector, is called speed and can be calculated directly from the coordinates of this vector using this classical formula. Again, back to the initial position. Display the speed value and observe how it changes. Again, back to the initial position. Add this small traffic cone and make the car drive towards the traffic cone. To make it possible, we need to find the displacement vector, shown now, which provides the relational position of the cone. Note that both the direction vector and the velocity vector must be aligned with the displacement. Mathematically, the displacement can be found by subtracting from our destination position, which is the traffic cone, the original position of the vehicle. A few other useful facts. The magnitude, or the length of the displacement vector, is the distance between the car and the cone. Knowing the distance and the speed, you can easily find the time the car needs to reach the cone. With this formula, we take a simplifying assumption the speed is constant, so there is no acceleration and no deceleration. Now, more interesting, The normalized direction vector, our short blue arrow, can be found by normalization of the displacement vector, the operation of dividing the vector by its own magnitude, in this case, the distance between the car and the cone. The direction vector multiplied by speed gives the velocity vector. And in case you already have the velocity vector but want to go back to the direction vector, simply normalize it. In case of the velocity vector, it's dividing it by speed, because the speed is the magnitude of the velocity. It is quite a complex sentence, but it makes sense if you think about it. One last thing. Imagine that we have this car casually driving across our game world. At some interesting moment, we would like to know whether we have already passed the traffic cone or it's still ahead of us. To discover that amazing truth, we need to consider two vectors. One of these vectors is the velocity vector. It will determine our front heading. You could take the direction vector as well, or even some displacement vector if it is aligned with the direction of the movement, but in this case the velocity will be the simplest option. The second vector must be displacement of the cone. It must be the relational position of the cone to the car, not an absolute one. Absolute position would be an absolute disaster. Now we can find the dot product of the two vectors. It is -12. The value less than 0 suggests that both vectors are pointing in different or divergent directions, so the cone is already behind us. That's all for now. Don't forget to explore more materials, such as these splendid and useful formulas, available in Canvas.